Welcome back to past paper walkthrough. Today we're doing GCSE Chemistry, higher tier. This is the paper at November 2021. It's paper 1, you have 1 hour and 45 minutes, and you're allowed a calculator and the periodic table they supplied to you, which I probably should get ready, but I do not have a periodic table with me at the moment. I'll see you when I need to draw it up. But anyway, question 1 is about carbon compounds. So fullerenes are carbon compounds. What is the shape of Buckminster fullerene? So this one, if you've remembered from your lessons, hopefully your teacher has told you this. It should be spherical. They're called buckyballs for a reason, and I think the answer could be spherical, could be ball shaped. Football probably would be edge case, but I'm not sure what the mark scheme wants from you, but that's that. Give one use of fullerene. So fullerene is used depending on their structures. They have different uses. So one of the more common use is a lubricant. So spherical fullerenes like Buckminster fullerenes can be used as lubricants in place of graphite, which is also a type of lubricant. So now this is, I suppose it's still question 1. Propanone is a compound of carbon, hydrogen, and oxygen, and there we have a dot and cross diagram. It's also commonly called acetone, which is very commonly used in lab as a cleaning solvent. So complete figure 2 to show a propanone molecule. So you can see this one is a displayed formula with all the carbon written out rather than a skeletal one. So we have to draw out the 2 carbons on 2 sides and then make sure that each carbon is tetravalent. So the middle carbon here, we have 1 single bond on the left, 1 single bond on the right, 2 bonds to the oxygen. That's a total of 4, and that's fine. Whereas on the edges that we've just added, we need to add hydrogen to it to make it tetravalent, which is 1, 2, 3 more bonds per carbon. So that gives us a total of 4 bonds per carbon, and each of them are bonded to a hydrogen atom. So there's a total of 6 hydrogens, and that's our displayed formula. And you can double check here, we have 1, 2, 3 hydrogens on each carbon, and each shared electron pairs is 1 single bond, right? So there's 3 bonds coming out of the carbon, and we have 1 bond coming from carbon to carbon, and that should fit this description down here. 1.4, determine the molecular formula of propanone, which is acetone again. So we just essentially count, right? So we start with the number of carbons, we have 3, so C3. Number of O's, there's 1, so O1, 1 doesn't need to be written out. And then hydrogen, we have 6, so H6, and that would be fine. You can do C3H6O, you can do H6C3O, you can do OH6C3. All of those are fine, it doesn't actually matter all that much. 1.5, we have propanone is a liquid with a low boiling point. Why is it so? So this is the classic, why does water have a high boiling point, and why does acetone have, methane have a low one? Remember when we're looking at simple molecular molecules here. So simple molecules are determined by their boiling point, their physical properties are determined not by their covalent bonds, it's by their intermolecular forces. To have a low boiling point, the intermolecular forces have to be weak, and therefore the last option is the correct one. You can't say the same for diamonds because they're giant covalent structures, and you can't say the same for sodium chloride because they're ionic structures. Okay, it only applies to simple molecular. 1.6, we have graphite. As GCSE questions go, graphite is probably the most commonly shown structure in exam papers. So explain why graphite is a good conductor and why it is soft and slippery in terms of structure and bonding. So there are a few key aspects of graphite. You know that it is carbon bonded to 3 other carbons, which means that each carbon have the ability to bond to or have a lone pair of electron which can bond to something else in theory, but it's not bonded. So these are all trivalent carbons, and each carbon have delocalized electrons, right? So the delocalized electrons is one thing, which means that they can go across the plane. So electrons here can go across that way. But for graphite, there's a different behavior, which is that the electron can move across layers if subjected to current, which means that what we need to say here is electrons can move across layers of graphene. So one layer of graphite is called graphene. So that's why it's a good electrical conductor, right? So that's the first 3 marks. Essentially, you have each carbon bonded to 3 other carbons, and therefore they have 1 electron pair of free electrons that can be delocalized and can move across the different layers of graphenes, and hence it is a good electrical conductor. That's 3 marks. Soft and slippery is less a property of electrons but to the actual structure. So the layers of graphene are not bonded to each other by covalent bonds. So you can see here up on the diagram, you can see all the covalent bonds are in hexagons, as we would expect in, say, benzene or something. But this time, these carbons do not have any vertical bond. The bonds between the layers are all van der Waals based, so they're not covalent linkages. It's all electrons. So that means that the layers of graphene can slide and hence they can behave slippery. And this is also why they can be used as lubricants at specific places. So I think the AC to DC converters in electronics actually have graphite connectors because they're slippery and they conduct electricity. So these are the other 3 marks. So you've got 3 marks from this section and you have 3 marks from this section. And that's the first question. Question 2 is about atomic structure and the periodic table. Gallium has 2 isotopes. So what are isotopes? So isotopes are atoms with well, we should probably say that atoms of the same element which contains different number of neutrons. So you can have a carbon-12 and a carbon-13. So carbon-12 contains 6 neutrons, carbon-13 contains 7 neutrons. And they are isotopes of each other. So that's the gist. You cannot have an isotope between, say, an oxygen and a carbon because they're not the same element and they're just different. Right, 2.2, we have a simple calculation of mass. So relative atomic mass is just the mass number weighted with abundance. So we know that we have 60%, so 60 over 100 of all atoms are 69 mass, and 40 out of 100 atoms are 71 heavy. And this is when I need to go find my calculator because I'm not prepared. Let's see, 69 times essentially 0.6 plus 71 times 0.4 gives me 69.8, which is the RAM. And that's as simple as this question goes, I guess. Gallium is group 3, so give the number of electrons and neutrons in the isotope of 69, or gallium-69. So remember, the top left number is the relative mass and the bottom left is the atomic number. Atomic number equals the number of protons. This is an atom, which means the number of protons equal to the number of electrons. So this is just a simple read of 31. It's just straight up copy and paste. And then neutrons is the difference between the mass and the atomic number, because the atomic number equals the number of protons. And the mass is the total number between protons and neutrons, which means that 69 minus 31 should give you 38. So that's the number of neutrons. The most likely formula of gallium ion, we know that it is in group 3. Yeah, it's given you the question. It's also on your periodic table. So the most likely ion is if it's fully ionized, and that would be gallium-3. In theory, I think gallium-1 is also a decent ion, but we don't need to go there. gallium was discovered 6 years after Mendeleev published his periodic table. You need 2 reasons why gallium helped the periodic table to be accepted. So one of the reason why gallium is accepted as, or gallium help the periodic table being accepted, is because the periodic table has preemptively estimated or predicted the existence of gallium before it's even discovered. So just to put it in word is so gallium was predicted to exist by the periodic table. So the periodic table already have a gap for gallium before it was even a thing. So that's the first reason. The second reason is that gallium actually behaved very similarly to however Mendeleev had grouped group 3 elements. So has similar properties. Did I spell this right? Yes. 2, 3 elements. Right, so the key thing about Mendeleev's periodic table was that not only it predicts gaps in the periodic table, the elements are all grouped up according to physical properties and chemical properties. So that's why all alkali metals behave similarly. Added to water, it fizzles and probably explodes. Halides all react with sodium or group 1 metals, and noble gases all are gases, and so forth. And gallium is similar to other group 3 elements, so that's why it also supports the theory, I guess. Question 3 is extraction, actually. So that's element R, which is being reduced from the oxidized form, and we need to calculate the relative atomic mass of R. So we know that 3 lots of H2 is 1 plus 1, or 1 times 2, plus R plus 3 lots of O, which is 3 lots of 16, is equal to 150. So what you need to do is just to do simple algebra, really. So 3 times 2 is 6, and so 6 plus R plus 48 is 150. And I am not very good with math, so I'm just gonna use the calculator, and that's 96, right? So R is 96, AR, and now it is time for us to go find the periodic table that I so very conveniently forgot. Google is my friend here. I just need to find something that's 96, so it should be pretty low down, but not that far. 95.95 is the one that I found, which is molybdenum. And so essentially it's this is in the transition metal block, and it's the period 5, and the third it's technically group 6, but it depends on how AQA defined its groups. It might just not be in group 6. It's complicated. Sometimes people sometimes the group doesn't go across in sometimes the group number just ignore transition metal block, and like some people say nitrogen is group 5. I tend to call it group 15, but that's just me, I guess. So this answer should be, are we meant to write, I guess we should write the full name. No, I think, oh, is there an I in there? Probably. Oh no, there isn't an I in the middle, so that's the right spelling. Much of chemistry is just spell the correct words, so it's a bit of a faff, but there you go. Carbon is used to extract tin from tin oxide. Calculate percentage atom economy. So atom economy is the weight of the product over the weight of all reactants, which is tin divided by tin oxide plus carbon. And in this case, that would be tin is 119. Thank you for providing that number for me. And we know tin oxide is 119 plus 2 lots of 16 is 32. And carbon is 1 lot of 12. And that, again, we use our lazy calculator. Make sure you do not forget about the brackets when you're doing the addition. Or in other words, please just use the calculator correctly. And that should give you 0.73006 or something. It doesn't matter actually. And in percentage, this is 73% to essentially 2 sig fig. You can do 3 significant figures, so which would be 73.0%. Does it actually matter? I don't think so. I don't know how they want to mark you, to be honest. I wouldn't really care, to be if I was marking. Right, tungsten is a metal. It's extracted from tungsten oxide. And this is essentially just separation question. So you can use carbon. It's cheap and it makes tungsten, CO2, and tungsten carbide. Tungsten carbide is actually a really useful material, but it's also really brittle. Second method is use hydrogen, and it costs quite a lot. I think you need to do some like expensive catalyst or something, but that gives you tungsten metal and water vapor only, which is very clean. And the third method is using iron. Now, iron is pretty cheap because it's I can't remember exactly how much of the Earth's crust, but it's pretty high in percentage, and it's cheap, so it's pretty good. Although you do make 2 solids, 1 tungsten and 1 iron oxide, which could be difficult to extract or remove from your tungsten. So evaluating the 3 different methods, we can say that essentially the first method, this is quite hard to condense into 4 marks because I can say a lot about each of it. But that also means that you don't need to talk about absolutely everything here. So the first thing you probably should think about is cost analysis. Is that 1 and 3 are cheap, and it's, I suppose the reaction itself is not too difficult. You don't really know that though, because I'm using my extra knowledge from not GCSE, so you probably don't know much about these reactions anyway. We know that 1 and 3 are cheap because it's given to you, and in terms of purity, we can say that 2 is best, as water is I suppose release as a gas, right? Which can be essentially vacuumed out or displaced by some other gases. And this gives you pure tungsten. Whereas 1 is probably decent, but it also makes, actually 1 is the worst one here in theory, because you have a mix of 2 tungsten containing compound that are solid. Right, so separating a solid from a solid is a pain, especially when both of them contains the same thing. Whereas for 3 is mediocre because again it contains 2 solids, but the good thing is iron oxide can be magnetized, so I would probably say that if I were to do it industrially, I'm gonna use iron because I can probably get pretty pure tungsten metal out by just removing the iron oxide after the procedure. They would probably form fine powders after the process, and you can just essentially run a big magnet, electromagnet through your powder, and all the iron oxide is going to get removed from your tungsten, and you'll end up with like some tungsten powder. So that's mostly what you need to be able to talk about. And these essay type questions are always don't do what I did here, which is just to summarize. You can say more about it, but please do check your time. You don't have all day. Just beware of how much time you need to do the rest of the paper. Right, so I've already done 30 minutes here, so I'm gonna pause here and we'll continue the next part in the next video. And for now, thank you very much for watching, and if you have any questions, do ask me in the comments below, and I will see you next time.